Okay, this is the next further maths lesson. It covers chapter 1.7 in the Year 13 Core Pure book. And what we're going to look at is we're going to look at an application of the nth roots of unity and the nth roots and the sort of geometrical aspect of them, and use that to actually help us solve some geometric problems by thinking about when you go from one nth root of unity to the other, what's kind of going on. So let's remind us when we had a look at the nth roots of any complex number. If you remember, we drew some R-down diagrams to show what they looked like. Remember, with nth roots of unity, all of those were spaced equally around a shape that had the same number of vertices as the number n. But the nth roots of unity all sat on a unit circle, and they all started on the real axis at 1. Now, the difference that you had where you had any complex number is that basically the first corner of the shape, instead of laying on the real axis at 1, it laid at the nth root of the actual complex number that you were finding the nth root of. So do you remember when we drew our diagram? So we got our first corner, and then to get round to the next one, okay, we multiplied, well, we took that first complex number and rotated around by 2 pi divided by n, so 2 pi split into the number of corners that we need. So this example here is a hexagon, and it's the 6th root of 7 plus 24i. So we're going to get our first corner here by doing the 6th root of the modulus of that, and then dividing the argument by 6. And then remember, we rotate around by 2 pi by 6 because we need 6 corners, okay, which is equivalent to rotating by 2 pi by 3. And then they all sit on this circle, which has the same magnitude as the magnitude of the first root. So it's this property really that we're going to use to solve some problems sort of of a geometrical nature, okay. So it's remembering all of the things we've done to do with getting from one corner to the next. We multiply round by 2 pi divided by how many corners we need. Okay, so let's have a look at a first example then. So we've got here, we've got a point P, and it lies at one vertex, remember vertex is just corner, one corner of an equilateral triangle. The centre of the triangle is the origin. Okay, find the coordinates of the other vertices of the triangle. Okay. So what you certainly can do with things like this is to just quickly start by drawing yourself a little sketch. It doesn't need to be amazing unless, you know, if the question asks for a sketch, then obviously you need to take a little bit more time on, but we're just going to think about where that point P is going to go. So root 3 is going to be a bit bigger than 1, and then 1's going to be up here, so it's going to be somewhere like here. So that's my point P. It's going to be out there. Okay, so if we think about to get from P to the next corner, what we're going to need is we're going to need to rotate round by, to get to the next corner, we're going to need to rotate by, well, it's 2 pi all the way round. How many corners do we need? Triangle 3, so we need to rotate by that. So what I'm going to do first, because we're going to make use of complex numbers to do that, is I'm going to take the point P. Now as a coordinate, root 3, 1. As a complex number, root 3 plus I. Happy enough with that? Okay, and I'm going to use my calculator, and I'm going to convert that into exponential form, 2e to the I pi by 6. And I used my calculator to do that. Remember how to do it. You put it in complex number mode, you type in root 3 plus I, you press the option button, and then you're looking for that one. Do you remember that converts it? Okay, so to get to the next vertex, okay, we need to rotate by 2 pi by 3. That's what we've decided to fit 2 vertices in. So the complex number that represents that is going to be, remember, we're not changing the argument of it, the modulus of it, so we're just going to multiply by e to the I 2 pi by 3. Okay, so that's what we're going to multiply by. Okay, so if I call the next vertex, let's call it say Q, So q is going to be equal to p, which is my original one, 2e to the I pi by 6. And I'm going to multiply it by my rotation complex number. I'm going to pop that in my calculator as fractions. I get 2e to the 5 pi by 6 I. What's the question asking me for though? Oh, it's asking me for coordinates. So what I'm going to do is I'm going to switch that back into the complex number form a plus bi. Again, remember how to do that. You use your r theta button. Make sure you're in radians. You type in 2 angle 5 pi by 6 equals, and it tells you that. That's still not a coordinate though, so let's make sure I give the examiner what he wanted. As a coordinate, that's minus root 3 and 1. Okay, my other corner, all right, so let's look at my other corner. R is going to be taking Q, so 2e to the 5 pi by 6i, okay, times by another one of the rotation matrix. Show you working though with this, and that gives me 2e to the 3 pi by 2i. And again, use your calculator, that will tell you that's minus 2i, so that's actually down on the imaginary axis down here. Okay, so my r is going to be down here to make my equilateral triangle like that. So as a coordinate, 0, minus 2. Okay, right, now you'll see why for part B it's useful to draw yourself a sketch. Whether the question asks for it or not, it's useful to have a sketch for when you're doing things like finding the area of the triangle, because here's my triangle. I'm sorry, this is so hard to draw straight lines on here. You do it better than that. Here's my triangle. Okay, you can see with that the easiest way to find the area of that triangle, because we've got a sort of a natural base from P to Q, is just to use my half base times height. Okay, don't need to do anything more complicated than that because the diagram's helping us. Okay, so my base is from P to Q, and if you look at P to Q as coordinates, okay, for that one, they're both at the y-axis at 1, so it goes from root 3 down to minus root 3, so it's 2 root 3 is the length of the base. The height is this bit here, so the distance on the imaginary axis. Sorry, I've messed up a little bit. So that goes from 1 down to minus 2, so that's going to be a 3. So my answer is 3 root 3. So as I said, use your diagram for that. That's going to help you. Okay, so in previous years I've taught that example, and everyone was fine with that. So let me show you what they then threw into the exam. Okay, so this is a question from a previous A-level further maths exam, which if you'd been shown the previous example, it would have looked quite similar to you, to that one. Okay, so what we're dealing with here though is the complex number. Again, look, it's virtually identical. It's an equilateral triangle, okay, and the point A is 6 plus 2i. Now, you put that in your calculator and try and convert it into exponential form. Basically, it's not nice in exponential form. Okay, the argument is not an exact value. It's not a nice argument like the previous one. So, you sat in the exam, what's my alternative? Okay, some of the boys I spoke to after the exam got this, some of them didn't, because look here, we're looking for my answers in that form, but X and Y are real and exact, so I've got to keep in my exact form. Now we know to get to the next vertex, okay, we rotate by 2 pi by 3, don't we? We know that for the next vertex, and so for the previous question we did e to the I 2 pi by 3. Now, because this is not nice in exponential form, what I can do is leave a in that form, and instead of multiplying it by an exponential, I can convert that to the same form. Using my calculator, that is equivalent to minus a half plus root 3 over 2i. Use your calculator. So, to get to my next vertex B, what I can do, and this is, you know, this is quite clever, and this is the sort of thing you need to try and think about when an exam question pops up and it's a little bit different to what you've seen before. You need to think about, have I got an alternative way of doing this? And yes, you do. You can use exponential form or you can use A plus BI form. So what I can do to get B is I can multiply that by that, because at the end of the day I'm still multiplying to do that rotation, it's just in a different form. And what's quite nice is put that in your calculator, and your calculators are good enough to give you try typing it in double brackets, they're good enough to give you a nice exact form answer, just like that. And that's what the examiner was after. Okay, so then what I'm going to do is I need to get my next coordinate. So I need to take my coordinate B, and again I need to multiply by another one of this. So leave that in your calculator as your answer, multiply by that in a bracket, and again your calculator's really nice leaving stuff in exact form. Okay, and it writes it exactly like this. You're using the power of your calculator. So what that question has shown you is that sometimes you need to just do something a little bit different to what you might have been shown in an example. So remember, when you're working with complex numbers, you have the option to work in either the A plus BI form or the RE to the I theta form. So use the form that's easier for the complex number that you're dealing with. At the end of the day, to do that rotation, you multiply two complex numbers together. It doesn't matter whether they're both in this form or both in this form. Okay, right. Part B then, I'll just go on to the next slide. So part B, it now says, here's my triangle ABC using the coordinates that we got in the first part. D, E and F are midpoints. So for this question, you're going to have to draw yourself a diagram to see what you're dealing with. Draw yourself a decent diagram. So work out where the size of the real and imaginary bits of B and C to work out roughly where they are. Okay, so pause this and you do that. Right, now because my drawing on here is so rubbish, I have actually drawn one and scanned it in. So it looks like that. So you can see I've roughly, not exactly, but I've roughly worked out where A, B and C are, so that they, they are in the right position. D, E and F are the midpoints, okay, and the area of the triangle I want is that shaded region there. Now that's going to help me because spotting what's going on there is going to make my life easier. There are a couple of different ways of doing this question, but hopefully when you look at that diagram, you will notice that the area of the triangle DEF, because ABC is an equilateral triangle, it's basically a quarter of the area of ABC. Can you see each of the four triangles that this has been split into are all little equilateral triangles? And you only spot that by drawing the diagram. So draw yourself a diagram. Right, so let's focus on working out the area of ABC. Well, we know it's an equilateral triangle, so let's find out one of the side lengths. So it doesn't matter which one you do. I think I did side length AB. So remember what it is. It's the square root of the difference between the real bits. So you've got them written on the previous slide. So the difference between the real bits is that. If I just remind you, let me write it up here. So what is A? So A is 6 plus 2i. Okay, and B, just so you can see them on here, B is minus 3 minus root 3, that's the real bit, and then plus minus 1 plus 3 root 3i. It's always the trouble when you turn over a page, isn't it? Okay, so the difference between the real bits is 6 minus minus 3, and then minus root 3, so it gives me that, plus. Difference between the imaginary bits, 2 minus minus 1 gives me 3. And then minus 3 root 3 squared. Again, put that all in your calculator, use your brackets, your calculator very nicely brings out to you that length is 2 root 30. Now, because I haven't really got a perpendicular height, I'm going to use my half AB sine C. What's quite nice is, because it's equilateral, the two side lengths are both 2 root 30. Okay, angle between them, well, it's an equilateral triangle, so sine, oh, I shouldn't use 60 really, should I? I should use pi by 3 because we're in radians there. Okay, doesn't really matter, to be honest, just make sure you change your calculator between it, and that gives you 30 root 3. And this is the area, remember, of ABC. So my final bit for the question then is area of DEF equals a quarter of the area ABC, which is equal to 15 root 3 over 2. 3 marks. That was quite a lot of work, but I do think that you could have made it a lot more difficult for yourself if you didn't draw yourself a diagram and spot the link between these. Okay, there were some other ways of doing it. Another way of doing it is finding, if you say that's the origin there, okay, it's finding the area of DOF there and then timesing that by 3. It gives you the same answer. I think that's probably the easiest way of doing it. So, interesting exam question that does highlight, remember, you've got your exponential form and you've got your A plus BI form. Both of those you can use. Okay, one last example, bit of a weird and wonderful example that came from the textbook actually. Talking about an ant. So an ant walks forward 1 unit and then turns to the right by 2 pi by 9. Repeats this a further 3 times, show that the distance of the ant from the initial position is this. Okay, so let's think about what it's doing then. So if I was to think about it kind of in a complex number mode here, if he went forward 1 unit, so he'd walk forward like that, 1 unit, okay. If he turned right 2 pi by 9, okay, and sorry, just clicking on right 2 pi by 9, what you do then is walk forward by that, and this bit here is my 2 pi by 9, okay, and then he'd do it again like that, okay, because it says he does it a further 3 times, so he'd do it again like that, and then he'd do it again like that. Okay, and then what we're looking at is we're looking at the distance from the origin. So the distance we're going to be looking at for this. So if we can use complex numbers to help us with this, then you know that sort of going along and then moving and then going along in the next bit, we can just do by complex numbers by treating them the same as vectors. Okay, so if we think about what's going on here, all right, so at the end of the day, the distance here would be the same as if he turned left or if he turned right. It doesn't really matter. Okay, so the turning, okay, 2 pi by 9 and then going forward 1. The complex number that would represent that, well, it needs to have magnitude 1. I'm not going to bother writing the run, but if I write it in exponential form, e to the I 2 pi by 9 is something that has direction 2 pi by 9, okay, and magnitude 1. I could put a minus in because he's turning right, but like I said, at the end of the day, it's going to give us the same magnitude at the end. So if we think about adding together our complex numbers then, my first one is going to be the 1, that's forward 1 unit. My next one is going to be one of those. Now, when I go on to my next one, he's turning a further 2 pi by 9. So I'm going to get in the direction 4 pi by 9 in total. He's going to do another one. Okay, like that. So that is forward 1 unit, and then he does 1, 2, 3. What does that look like? Okay, that is a geometric series. Remember those? What we were doing when we were summing series, a geometric series. First term A is 1, my ratio e to the I 2 pi by 9. So, you know, to show that here, this, you know, it looks like some of the things that we were getting when we were doing those summing series. So hopefully that would have sort of prompted you to do this, okay? So we want to do the sum of the first 4 terms. Remember what the formula looks like, A r to the n minus 1. It is in the formula book over r minus 1. Let's put in our values. A is 1. R to the n, well, n is 4, so you get e to the I 8 pi by 9, because you times that argument by 4, minus 1 over e to the I 2 pi by 9 minus 1. Now, what we want to do now, the distance is going to be given by the magnitude of this thing here, but at the moment, do you remember when we were doing the other ones, we've got the problem of we've got i's in the denominator, so at the moment I need to simplify that. And again, do you remember questions we were doing before where I was looking at the numerator has got sine 4 pi by 9, so I need e to the I 4 pi by 9 to be able to do that. So do you remember what we did? We took out a factor. If I take out the e to the 4 pi by 9i, what I get in my bracket is a 4 pi by 9i here and a minus 4 pi by 9 here, okay? And the same with the bottom, I want sine pi by 9, so I need an e to the I pi by 9. So again, let's take out an e to the I pi by 9. So what I leave inside my bracket is e to the I pi by 9i minus e to the minus pi by 9i. Now, do you remember when we were doing those before? So I'm going to leave that the same. Okay. If I write my exponential form as sine plus cos, e to the 4 pi by 9i is sine cos 4 pi by 9 plus I sine 4 pi by 9. The other one is cos 4 pi by 9 minus sine 4 pi by 9. So what I get on the top is I get 2i sine 4 pi by 9. Okay? Because remember the e is cos plus I sine, the e to the minus is cos minus I sine. And what I get on the bottom is 2i sine pi by 9 for the same reason, okay, because you're not sure. This bit here I would write as cos plus I sine. This bit here would end up being cos minus I sine. So you'd end up with, because of the subtract in the middle, you'd end up with the cos's going and you'd end up with the 2i. So we're almost there. These bits here cancel. So what do I end up with? Let's just simplify this. E to the power divided by e to the power. Subtract the powers. I get e. Okay, if I subtract the powers there, I get e to the I pi by 3. What have I got left here? I've got sine 4 pi by 9 divided by sine pi by 9. Now have a look at what we've got here. This is in the form r e to the I theta. Okay, so this is my theta. That's my argument. This whole thing in the bracket is my r. Okay, so the magnitude of the sum, which is my distance, is the r bit, which is sine 4 pi by 9 over sine pi by 9, as expected. Okay, so if it asks for the argument or what direction it would be, because he has turned right, actually the argument would be minus pi by 3, but they didn't ask for that. Okay, so that has highlighted again with the summing series ones, which I know are quite tricky, that you have to look at what the show that is, so you can try and work out what things you need to take out as factors, so you end up with this whole bit, either the coses cancel or the sines cancel, depending on what values we've got in there. Okay, right, so I mean, if you struggle with that, rewind it, just have another look at it, have another go through it. Okay, over to you then. There's just 4 questions for you to do. I'm not going to ask you to submit these because you submitted the previous work, so have a good go at those, and then we'll have a talk about that when I next see you on Teams. Okay, thank you very much.